All right, this is homework number 6, question number 4 here. Oops, didn't share yet. Okay. And this one's a little bit tricky, but I think if we just go stepwise, things will be good. Let me pin my video so other people's video aren't stuck in the recording. Okay, so here we have a situation where we have 80 kilowatts of power to a town through transmission lines. We know the resistance through the lines. We want to determine how much the power is saved if we use a step up and then a step down. And that's transmitting the power at 120 volts. And we assume that each transformer is 99% efficient. So we need to make that modification on each one. And we're basically set up with two scenarios. And I'm going to illustrate those scenarios with a picture here. So this is homework 5. And this is question number 4. So Q4. Okay. So the idea is within the first scenario, there is no step up, step down, or any of that business, right? So what we have is a power total, and that's what's originating at the generator. So I'm just going to draw a box, call it gen for generator. And then we have the town, and I'll draw that as a circle, and I'll call this town, right? And we know the power delivered there is P1. So we'll say P1 is equal to that 80 times 10 to the third watts. We know the R is equal to 0.02. We know V1 is that 120 volts, and then V2 is when it's 30,000 volts. And then we know that it's 99% efficient, so you'll see me use that variable to represent that. So within this first scenario, all we have is a situation, here I should use white, is a situation like this, right? Where we have R here, and we know what the voltage acting here is, right? There is no step up, it's just V1. So the first thing we're going to need to solve for is what I1 is equal to. And to solve for I1, actually, I'm going to call this P1 prime, and we'll see why in a little bit. And to solve for I, we're going to need to use our equation like this, rearrange, solve for I, where I is going to be equal to P1 prime over V1. Okay, and that will come out to be some value. And for now, I'll just call it X, and I'll pause the recording and plug everything in, and I'll rewrite it. And then we need to also find the power that's lost through the resistor. So remember, with these kind of questions where we have a transmission line, a generator, a town, basically those words, that really cues you off to think you need to remember to find the resistance that's acting through the wire. Okay, so the total power then is going to be the power plus P1 plus the amount through the resistance. But to solve for that power through the resistance, which I'll call PR, we're going to need the current because we know what the resistance value is, right? They tell us R, but we don't know what this I is equal to. So we need to use I. Okay, so you solve now for PR. You plug in this variable right here over here, and you solve for PR. So PR will be equal to, let's just call it Y. Okay, and then at this point, you can solve for P total in this first scenario as going to be equal to P total. I'll say P total is going to be equal to that P1 prime plus PR. Okay, and then you're going to plug that in and solve for everything. So let me pause real quick and solve these numbers out, and I'll be right back. Okay, so then you will end up getting P total as such. Okay, so now we know P total, like I said, in this kind of first condition. And to mark that, I'm just going to call this A, and I'll do it in red so we're very clear. But now we're dealing with B, where we have a step up and then a step down. And this is what I said during the SI session, which thank you to those who went because you were able to solve this from before. But I mean, that's neither here nor there. So what is the step up, step down situation? That's basically what we see where we have a generator, and to that generator, it goes to these transmission lines, and those transmission lines upregulate it before it's stepped down, before it hits your house, okay? And the idea with the step up is there's going to be, it's going to be more efficient, right? So that means when you solve this way, you'll notice the values will come out bigger than in the other condition. But in this case, we're going to start with our generator again, and we'll call that P total, right? Because we know the P total actually is. So P total. And we're going to have this set up. And you draw it like this, actually. Okay? And then within this first area, it's going to be V1 because we haven't been stepped up yet. But then we have this transformer, which you draw like this. And it's called a step up. So I'm going to write down here, I'll do it in red. Okay, and we're going to have a step up. Okay, and what the step up does is it bumps that voltage way up. So now we're going to have V2. So we're going to have V2 here, and within V2, we have a resistor, because we know the resistance. We're going to have something that looks like this. I'm kind of drawing it all out to show you the steps, but I don't know if you would need to do this on it. So I don't know if you have to even worry about it. And then within here, we have V2, okay? Let me do this in orange. We have V2, but then we also, you can't forget about that resistor. And the power then here, all right, let me do that at the end. And then we have, again, the step down before it hits back to our house, right? We don't want to deliver the voltage at 30,000 volts to a house because that would be crazy if you like charged your phone. Okay, and then we have the power delivered to the town, or I keep saying townhouse. It's, you know, it's more or less the same thing, but we'll call that P1 prime again. And the reason why I call this P1 prime and not P1 is because at each transformer, there's a unique power. So between every single instance of step up, there's power. Between P3 and P2, we'll see, or let me do that first. Let me call this P2 and this P1. And then between P2 and P1, because there's that step down, there's going to be a difference in power. And then the relationship between P3 and P2 is just going to be the power plus the power through the resistor is equal to P2. So basically, at every instance where there's kind of I'm going to say circuit element, but you can think about that as a step up through the resistor or the step down, there's going to be a difference in power we need to solve for, right? And the reason why we need to solve for each one of those is because we need to solve for P4. And P4 tells us what do I want to solve? How much power is saved, because if you find the difference between P total and P4, you'll know the amount saved using one conformation versus the other, okay? There will be actually like less power lost. So I know that sounds like total word soup and I'm probably losing you, but essentially what we're looking for is P total, which we found, and then we need to find P4. And that change in power, that being P total minus P4, will tell us how much power is saved if the voltage is stepped up and then stepped back down. So how can we solve for P4? Well, we need to work from where we know the power. And we only know the power in this scenario with this P1 prime. So we start with P1 prime. Now, what's the relationship between P1 prime and P2? Well, actually, P1 prime and P1 are equal to the same thing. So that works out nicely. P1 prime and P1 are equal to the same thing. So we can now find what P2 is using that understanding. So we know that they're 99% efficient. What does that mean? That means P2 times 0.99 is equal to P1 prime. So therefore, P2 is equal to P1 prime divided by 0.99. Sorry, and I realize that's confusing, that I should have just called them both P1, but I guess like there could be an instance where there could be I don't know. This is how I like to set it up. Sorry, I should have been more clear. Okay, so now we can solve for P2. So also, if you're watching along online, if you wouldn't mind plugging that in, that'd be awesome, possum. Okay, so with understanding of P2, we can now find the current, and using that current, we can solve for I2. I'm sorry, we can solve for the current, and because we know V2, right? So now that we know P2, we can solve for I2 because we know what V2 is equal to. And using I2, we can solve for PR. That's the power lost through the resistor. Okay, so I don't want to jump too far ahead, but P2 is going to then be equal to V2 over I2. Okay, and like I said, we can now use I2 to solve for the power resistor prime. Okay, and that's going to be equal to I2 squared R. We can solve for P R prime. okay? And like I said, the relationship here is that P3 is going to be equal to P2 plus this power through the resistor, right? Because, you know, the power comes out like this. It hits the resistor and it goes through here before it stepped back down. So that means what it was here is going to be equal to the sum of these two. So now we have enough to solve for P3, where P3 is going to be equal to P2 plus PR, PR prime. Because we already solved for PR before, it's different. Okay, we know P3. Now, what's the relationship between P3 and P4? Well, we know these guys are 99% efficient, so we can solve for P4 using the fact that P3 is going to be equal to that 0.99 times P4, right? So then to reverse that 99% efficiency, we just divide, and we're now able to solve for P4 is equal to P3 divided by 0.99. Now, we'll get some value P4, which is going to be equal to, well, I don't know, it's going to be some big number. We'll figure that out later, but what we're looking for is the change in power in both scenarios. So we'll say, therefore, this change in power is going to be equal to power total, which we just found up here, that's what we have underlined in orange, is going to be equal to that minus P4. We'll underline that in green. Okay, so this change in power, well, it's going to be a positive value, first of all, because we expect it to the P total to be bigger than the P4. And we'll get some positive value, and that tells us how much power will be saved. The voltage is stepped up rather than transmitting the power purely at 120 volts. Okay, so let me pause and I'll write in the numbers. Or I mean, actually, I showed you how to solve it, no numbers. So this should suffice. And I'll take questions. All right, so now we're going to do question number 5. Was it 5 or 7? 7.
7.
And this one's actually pretty tricky also. Wow, this is a hard homework set. So we have this situation where we have a coil. We know the radius, resistance. It surrounds a solenoid. We know how many turns. We know the radius. And we want to find the length of the solenoid. Or do we know the length? The current changes. We know the change in current over time. So we have some expression for induced EMS, that being a change in induced current divided by a change in time. And what we're solving for is the induced current within the coil. Okay, so we have this like system where they're like with each other. So I think that's just really important that we just define our variables. So I'm going to make a coil category. I'm going to make a solenoid category, and I'll just call it C and S, but I'll do S first. S, so these are all the solenoid things, right? We know the length, 0.05 meters. We know the initial current, 0 amps. And then we also know the final. And S down here, again, solenoid. So whenever I label things like that, that's what I'm talking about. You know, time is 0.4. You know, the amount of turns the solenoid has. So that's equal to 2,000 turns. And we know the radius, RS, is equal to 0.08 meters, right? Yeah. And then we also have the coil, call it C. You know, the turns of the coil. Yeah, it's 200. We know the radius. We know the resistance. Oh. Okay. And what we're looking for is the induced current through the coil. So I'm going to say IC is our unknown. Okay. Like I said, the first thing we need to do is solve for that induced EMF equation. We're going to use starting the coil, right? Because through that coil, we can solve for this value, and then we can use like a manipulation on Ohm's law to solve for that current we're interested in. So our equation here is that minus N, and we're talking about the coil now. So I'm going to do NC, and it's going to be that change in the induced, or I'm sorry, that change in I divided by that change in T. Okay, and that's going to be of the coil. Okay. And then what that's how we can express that is the amount of turns of the coil is going to be the change in the field of the solenoid times the area of the solenoid divided by a change in time. Okay, And the area is not changing, so we can factor that out. Okay, I need to pause the recording because I want to make sure I get this right. Okay, sorry, I have to pause the recording just to make sure everything was going well, and we ended up working out. So, like I said, we're going to use this induced EMF equation, and we're going to have an induced EMF of a coil, right? So that's why we're going to use this equation, and that's just like the number of turns through it. That's that magnetic flux, and we're going to just kind of expand, and that's going to be the B field. That's going to be an external magnetic field supplied by the solenoid, and I kind of drew it out for us when I was explaining it, and it goes as such, where that blue is the B field through it. And what is magnetic flux? It's just like the field lines that are going through a surface, right? And some of them go through it, some of them don't. And the number that do go through it is what we call the magnetic flux. So it's basically just a way to measure how much flux is going through some surface, right? Or in this case, a coil. Oh, I saw a cat on a camera. That's very cute. Oh, he has a cone on.
Yeah, eye infection.
Oh no. That's funny. Okay, so we have an induced EMF on a coil, and we know it's going through. So we need to find that magnetic flux, but we're dealing with a solenoid. So we're going to use that B field through a solenoid equation. That's what we do, that substitution right here. And right here. And we plug it in, factor out what we can, such that what's only remains is what's changing over time, right? So we have a change in the current over a change in time. You substitute everything in, I'm sorry, not substitute, plug in everything and solve, and you end up solving for the induced EMF equation, right? And then finally, you do a modification on Ohm's law. Don't forget the absolute value here, and you solve for the I induced. Something that we realized is this RC here is kind of a red herring, right? It like tips you off, like maybe I need to use it, but you actually don't need to use it, just to trick you. And also the answer key is wrong. So that's probably another reason why this one's very confusing. So that's what your answer should come out to be. And I think there seems to be a lot of confusion, like not seems to be, like I was getting messages about this, like what each equation is. Like our induced EMF for a coil, right? Induced EMF for a coil, that's this equation over delta T, right? And sorry, like sometimes people write it like this. I write it like this, but it's kind of the same thing. And what this guy is right here is magnetic flux, okay? So this dude right here is going to be equal to BA cosine theta. But don't worry about theta, it's normally equal to 0 degrees, so it ends up becoming 1 anyway. And when you plug it in, what you're worried about is a change, right? A delta. So there's a few ways by which you can adjust magnetic flux. There's 3 ways, actually. It's a private message here. Oh, we're talking about a cat. There's 3 ways that you can adjust magnetic flux. So you can either change the magnetic field magnitude, that'd be like increase it or decrease it. You can expand the loop, so you make the area bigger or smaller, or you can actually change the angle of the loop. Changing the angle of the loop's pretty complicated. I think it might be above this class, so don't worry about that. I mean, just keep in your back pocket that it can exist. But it's normally a change in B or a change in A. It's very important. So then when we expand this equation like we do up here, in this case, we're having a change in the B field, right? Because we have a change in current. But had it been that we're having a change in area, you will factor out the B and you will leave in the A, right? So it's what's changing stays there, and what's changing over time is what's really important. So don't forget that. And then the final thing, like I would feel would be like foolish to not add is there's a special condition when there's an induced EMF in a conductor moving through an electric field. So conductor moving through an electric field, that's basically like a metal loop, a rectangle or square. If you see rectangle or square, you can immediately solve for the induced EMF using the induced EMF is going to be equal to the B field that's acting there, the velocity at which it moves, times the length that's going to be moving up and down, right? So it'll be like some situation where it's like this. Oh, some situation where it's like this, where that's field, and you're gonna be moving like this, and this is going to be equal to L. Okay, so that's a special condition that you can use. But I mean, this was kind of the main point. Sorry, I kind of went off on a tangent there, but I just want, it needs to be clear that we do this. Okay, I'll take questions, and then we'll move to the next question. Okay, so question number 8. At first I wasn't going to record it, but then it seems like it's a good one to go through. And I actually did get stumped for a little bit, so thank you to for the help that someone shouted me out with. Okay, so we have a situation where a rod is moving down, right? So that means the field that's through this loop is going to be getting bigger. And because that area is getting bigger, we're going to have more B field going through that loop, right? And that means that through Lenz's law, the current through the wire will flow a direction that creates a magnetic field that will cancel out that original increase in the magnetic field per its area increasing, right? So basically, since there's more going in, to cancel it out, we want to have more going out. And because it's more going out, it's got to be counterclockwise induced current, right? And because we have a counterclockwise induced current, we can now find that direction of the magnetic force, where if we like, maybe we should redraw this like this. We know the rod is of some mass M, FB pointing up, MG pointing down, and we know the direction of induced current. Call that positive and that like that. We can now work to solve for that. What do we mean? Velocity? Yeah, the velocity, right? So the first thing we need to do is solve for I induced, because we know we're going to need to use that I induced when we substitute back in our equation for FB, right? So that's just going to be equal to E induced. And this is that special case where we can use that BLV, right? And we know what BLV is equal to BLV. I should probably write it like this. E induced is equal to that I induced R, and that E induced is also equal to, I'm going to draw it up here, BLV. So now we can make a substitution. BLV is equal to I induced R. We now have an equation for I induced. And we can now use Newton's second law to solve for all the forces in the y direction. We know that acceleration is going to be equal to 0. We look at our diagram, we'll see FB minus mg is equal to 0. We now can solve for FB is equal to mg. FB, we know what FB is constituted by. That's that I induced L cross B. That should be something we remember from before. And that length, I call it D. So I induce D. Sine, cross product tells you sine, the angle between them is 90 degrees, so it's equal to 1. So just B. We know what I induced is, we solved for that before, BLV over R. And then we just got to multiply in that big B. And we got to rearrange to solve for V. And when you rearrange here, so let me just do that real quick, actually. B squared. And now D squared, because remember I called LD in my diagram. V over R is equal to mg. We want to solve for V alone, so therefore V is going to be equal to mgr, and then divided by B squared D squared. Okay, so no number solution here. Okay. So yeah, the key idea is, and what was stumping me for a second, I just couldn't figure out why, is that we're going to be having an increasing area, right? As this rod goes down, the area within here gets bigger, and that means more field can go in. That means the current of the wire must flow in a direction that creates a magnetic field. So right-hand rule number 2 coming out of the page, that cancels out that original increase in the magnetic field, right? So because we have more field going in, we need to have more field, an increasing field coming out, which we can use right-hand rule to know that it's going to be going eastward through the wire. So heading this way, eastward through the wire, or counterclockwise with respect to the whole system. And that's how we answer part A. And then we've already gone through this part. And I think the key thing to remember is that we have a modification on Ohm's law here. that when we have a square or rectangle moving through a space, we can use this BLV equation that really cleans it up and allows you to solve a lot faster. Okay. So I'm glad we were able to review this one. This is a good practice. So we had another good point brought up that is worth mentioning. When we see the term long period of time, we're able to assume that acceleration in the y direction is going to be equal to 0 here. So that allows me to bump this guy out equal to 0 and then set FB equal to mg. Another thing to recognize is that in these questions, often we're told it's at equilibrium. So that means, you know, like the net force is equal to 0. So again, acceleration is equal to 0. But I think in either case, we should be able to predict that we're going to be setting this equal to 0 here. And that's kind of fundamental to solving this. So thanks for reminding me to bring that back up.